Hello students, I am Mrs. Anuradha Desai. I am Assistant Teacher of Chemistry in Satish Pradhan Gyan Sadhana College. Today we are going to learn Ionic Equilibria, which is a newly added chapter in 12th standard syllabus. It is very easy and scoring chapter. So let us start. In this chapter, first of all we will see what are electrolytes. The substances which give rise to ions when dissolved in water are electrolytes. There are two types of electrolytes, strong electrolytes and weak electrolytes. Strong electrolytes ionize completely. Examples: strong acids, strong bases, salts. While weak electrolytes, they dissociate to smaller extent. Examples: weak acids and weak bases. It is only weak electrolytes which dissociate partially in dilute aqueous solutions, establishing equilibrium between ions and non-ionized molecules. See students, here we have seen weak electrolytes, they dissociate to smaller extent. The meaning of this is the dissociation reaction is a reversible reaction. Of course, there will be a forward reaction as well as backward reaction. When the rate of forward reaction becomes equal to the rate of backward reaction, we say that the equilibrium is achieved, which is not possible in case of strong electrolytes as they ionize completely. After this, we will see the meaning of degree of dissociation. The symbol is alpha. The degree of dissociation is defined as the fraction of total number of moles of electrolytes that dissociate into its ion when the equilibrium is obtained. Okay. See the formula. Alpha is equal to number of moles of electrolyte dissociated upon total number of moles of electrolyte. Suppose you have taken 100 moles of electrolyte. So what is the total number of moles of electrolyte? It is 100. So 100 will come in denominator. Now suppose at equilibrium out of 100, 50 moles get dissociated. So 50 will come in numerator. So alpha value will come 50 upon 100, that is 0.5. Alpha will become 0.5. Suppose you have taken 500 moles of electrolyte. So total number of moles will be 500. 500 will come in denominator. Out of that, suppose 100 moles of the electrolytes dissociate at equilibrium. So 100 will come in the numerator. So 100 upon 500, the answer will be 0.2. Okay. Now, the next concept is percentage dissociation. The formula is very simple. Once you calculate alpha, just multiplied alpha by 100, you will get percentage dissociation. Yes, one more concept. By using this alpha value, you can calculate the equilibrium concentration of cation or anion by a formula alpha multiplied by C. Now, what is C? C is a molar concentration of the electrolyte. Mostly you will get the problems based on this concept where they will ask you to calculate degree of dissociation, or they may ask you to calculate the equilibrium concentration of cation or anion. Okay. And a simple question like this also they can ask, that is define degree of dissociation. Now we are going to study about acids and bases. The first theory is Arrhenius Theory. According to this theory, acid is a substance which contains hydrogen and give rise to H plus ions in aqueous solution. For example, you can take a simple example like hydrochloric acid. HCl in aqueous solution, it gives you H plus ions plus Cl minus ions. Similarly, you can predict the definition about the base. Base is a substance that contains OH group and produces hydroxide ions in aqueous solution. For example, simple base, you can take NaOH. So NaOH in aqueous solution will give you Na plus OH minus. Now we will see what are the drawbacks of this Arrhenius theory. The Arrhenius theory is applicable to aqueous solution. See here in both the definition, in acid and as well as in base, in both the definition, aqueous word is very important. That means Arrhenius theory is applicable only to the aqueous solution, and it does not account for the basicity of NH3 and Na2CO3, which do not have OH group. On Arrhenius theory, you may get a very simple question like define acid and base according to Arrhenius theory. Or you may get a question like give the drawbacks or limitations of the Arrhenius theory. The second theory which we are going to see is Bronsted-Lowry theory. According to this theory, acid is a substance which donate proton, that is H plus, to other substance, while base is a substance which accepts a proton from the another substance. For example, you can write a simple equation like HCl plus NH3 will give you NH4 plus Cl minus. Here what is happening? Just see here. HCl is going to lose a proton and NH3 is going to accept that proton. So HCl will be converted into Cl minus while NH3 is converted into NH4 plus. In this particular example, HCl is acid and NH3 is base. HCl loses its proton and forms Cl minus. So, Cl minus is known as conjugate base of the acid HCl. Similarly, NH3, it accepts proton from HCl, it forms NH4 plus, which is acid. So, we can say that NH4 plus is conjugate acid of the base NH3. So here there are two conjugate acid base pairs. First one is HCl, Cl minus. Similarly, the second one is NH4 plus and NH3. This is the explanation regarding conjugate acid base pair. You can go through it. On this, you may get a question like define acid and base according to Bronsted-Lowry theory. Or you may get a question like what is conjugate acid base pair? Give one example. Now this is third theory, that is Lewis theory. According to this theory, acid is a species that accepts a shared pair of electron, while base is a species which donates a shared pair of electron. Mentioned example, that is ammonia, when it is reacting with boron trifluoride, it forms ammonia boron trifluoride complex. Here what is happening? If you look at ammonia, nitrogen is a central atom. It has a lone pair of electron. While boron trifluoride, boron is a central atom and it has incomplete octet. It requires 2 electrons to complete its octet. So, nitrogen, it donates its lone pair of electron to boron, forming a coordinate bond, and the complex formed is known as ammonia boron trifluoride complex. So, here we have studied 3 theories under acids and bases. The first one is Arrhenius theory, second one is Bronsted-Lowry theory, and now the third one is Lewis theory. On this, you may get a simple question like define acid and base according to Lewis theory. Give one example. After this, we are going to learn amphoteric nature of water. See, water has a capacity to act both as acid as well as base. I have given you 2 examples. In the first example, in the first equation, you can see that water is reacting with ammonia so as to form hydroxide ion and ammonium ion. So what is exactly happening in this particular equation? Water is losing its proton while ammonia is accepting a proton. So according to the definition, water is acting as acid. While in the second equation, when water reacts with HCl, what is happening? water is accepting a proton from HCl, hydrochloric acid, and it forms hydronium ion and Cl minus ion. So with two different reagents, water is acting differently. In the first equation, it is acting as acid. In the second equation, it is acting as base. So water has a capacity to act both as acid as well as base. It is known as amphoteric nature of water. On this, you may get a simple question like explain amphoteric nature of water. Now we are going to learn dissociation constant of weak acid and weak base. A dissociation constant of weak acid and weak base is defined as the equilibrium constant for dissociation equilibrium of weak acid and weak base respectively. Consider Ha as weak acid. As it is a weak acid, it dissociates to a smaller extent, giving you H++ A-. So the dissociation constant of weak acid Ka is equal to molar concentration of H plus into molar concentration of A minus upon molar concentration of Ha. Similarly, for weak base BOH, it will reversibly dissociate as B plus OH minus, and the dissociation constant of weak base Kb will be equal to molar concentration of B plus into molar concentration of OH minus upon molar concentration of BOH. On this, you may get a question. Define and derive the expression for dissociation constant of weak acid and weak base. What is expected? Definition and expression for both. After this, we are going to learn Ostwald's dilution law. Again, we are going to consider a weak acid Ha, reversibly giving you H plus A minus. As previously studied, Ka is equal to molar concentration of H plus into molar concentration of A minus upon molar concentration of Ha. Suppose now 1 mole of weak acid Ha is initially present in volume V of solution and alpha is a degree of dissociation. Then amount present at equilibrium. How to calculate amount present at equilibrium? If alpha is a degree of dissociation, you know that out of 1 mole of Ha, alpha will be dissociated. If alpha moles get dissociated, that means you will get alpha number of H plus and alpha number of A minus. Okay, so number of moles of Ha undissociated will be 1 minus alpha. This is amount present at equilibrium. Now we are going to calculate the concentration at equilibrium. How to calculate concentration at equilibrium? If we divide amount present at equilibrium by volume, we will get concentration at equilibrium. As volume is V, the concentration at equilibrium in moles per dm cube. For Ha it is 1 minus alpha upon V. For H plus it is alpha upon V. Similarly for A minus it is alpha upon V. Substituting in equation 1, we will get Ka is equal to alpha upon V multiplied by alpha upon V divided by 1 minus alpha upon V. If we simplify that, we will get Ka is equal to alpha square upon 1 minus alpha multiplied by V. But we all know that C is equal to 1 upon V. So we can substitute, instead of 1 upon V, we can write C. So we will get the another equation, that is Ka is equal to alpha square C upon 1 minus alpha. Now for weak acid, alpha is very small. Therefore, the equation 1 and 2 will become as Ka is equal to alpha square upon V, or Ka is equal to alpha square multiplied by C. Thus alpha is equal to under root of KAV or under root of Ka upon C. Thus, the degree of dissociation of weak acid is inversely proportional to the square root of its concentration or directly proportional to the square root of volume of the solution containing 1 mole of weak acid. On this, you may get a question, derive Oswald's dilution law for acetic acid. Here what is expected? See, here they have specified for acetic acid. Again, instead of HA, you are going to write the equation for acetic acid, that is CH3COOH. Or you may get a question, derive the relation between the degree of dissociation alpha and molar concentration of C for acetic acid. For weak base, just now we have studied for acetic acid, that is a weak acid. Now we are going to study for weak base. For weak base, again we are going to consider 1 mole of weak base BOH. Now it is base, so we are going to use the symbol BOH. So 1 mole of weak base BOH dissolved in V volume of solution, and alpha be the degree of dissociation. As it is a weak base BOH, you can write the equation BOH reversibly, giving you B plus OH minus. Amount present at equilibrium, definitely as alpha is a degree of dissociation, number of moles of B plus alpha, number of moles of OH minus alpha, and number of moles of BOH undissociated will be 1 minus alpha. Now concentration at equilibrium. For BOH it is 1 minus alpha upon V, for B plus it is alpha upon V, and for OH minus it is alpha upon V. Now we know that Kb is equal to molar concentration of B plus into molar concentration of OH minus upon molar concentration of BOH. Substituting the values, we will get alpha upon V multiplied by alpha upon V divided by 1 minus alpha upon V. If we simplify that, we will get alpha square upon 1 minus alpha into V. As we all know, C is equal to 1 upon V. We can write Kb is equal to alpha square C upon 1 minus alpha. Again, as it is a weak base, you know that alpha is very small. So 1 minus alpha is approximately equal to 1. So the equation 1 and 2 will become Kb is equal to alpha square upon V, or Kb is equal to alpha square C. That means alpha is equal to square root of Kb into V, or square root of Kb upon C. Thus, the degree of dissociation of weak base is inversely proportional to the square root of its concentration or directly proportional to the square root of volume of the solution containing 1 mole of weak base. On this, you may get a question, derive the relation between degree of dissociation alpha and molar concentration for NH4OH. Now NH4OH is a weak base, so instead of BOH you are going to use a symbol NH4OH and you are going to write the complete derivation. After this, we are going to see the auto-ionization of water. Pure water, it ionizes to very small extent. We can write the simple equation as 2H2O in liquid form. It will give you hydronium ion, that is H3O plus OH minus. So the equilibrium constant for the above equation, it will be K is equal to molar concentration of hydronium ion multiplied by molar concentration of hydroxyl ion upon molar concentration of water raised to 2. Because if you see the equation, we have taken two molecules of water giving you one of hydronium and one of hydroxide ion. Okay. Now, if we take the denominator H2O liquid raised to 2, molar concentration of water raised to 2 on left hand side, we will get K multiplied by molar concentration of water raised to 2 is equal to molar concentration of hydronium ion multiplied by molar concentration of hydroxide ion. As majority of water molecules remain undissociated, the concentration of water we can treat it as constant. That means it will be another constant. We can take it as K dash. So K multiplied by K dash is equal to molar concentration of hydronium ion multiplied by molar concentration of hydroxide ion. If we substitute K multiplied by K dash as Kw, we will get the equation Kw is equal to molar concentration of hydronium ion multiplied by molar concentration of hydroxide ion, where Kw is the ionic product of water and it is defined as product of molar concentration of hydronium ion and hydroxyl ion at equilibrium in pure water. Now, in pure water, we all know that the molar concentration of hydronium ion is equal to the molar concentration of hydroxyl ion. So, at 298 Kelvin, the concentration is found to be 1 into 10 raised to minus 7 mole. Therefore, substituting that value in the equation, we will get Kw is equal to 1 into 10 raised to minus 7, that is for hydronium ion, multiplied by 1 into 10 raised to minus 7, that is for hydroxyl ion. What will be the answer? It is 1 into 10 raised to minus 14. So, Kw value will become 1 into 10 raised to minus 14 at 298 Kelvin. Now, we are going to learn about pH scale. First of all, we will try to learn the meaning of pH. The meaning of pH is potence of hydrogen. That means it gives us the idea regarding H plus ion concentration. The concept of pH was first introduced by Sorensen in 1909. He defined the pH of the solution as the negative logarithm to the base 10 of the concentration of H plus ions in the solution in moles per dm cube. The mathematical equation is pH is equal to minus log to the base 10 of molar concentration of hydrogen ions. Now, from this expression as well as from the definition, you will come to know that if the hydrogen ion concentration in the solution is less, pH will be more. Vice versa, if the hydrogen ion concentration in the solution is more, pH will be less. Now, similar to that of pH, we are going to see the meaning of pOH. What is the meaning of pOH? Of course, it will be the potence of hydroxide ions. So, the definition is, it is defined as the negative logarithm to the base 10 of the molar concentration of OH minus ions in the solution in moles per dm cube. Mathematical expression, pOH is equal to minus log to the base 10 of hydroxide ion concentration. That means if OH minus ions in the solution is less, pOH will be more. Vice versa, if OH minus ion concentration in the solution is more, pOH will be less. Now we are going to learn the relation between pH and pOH. See, for any solution we can calculate pH as well as pOH. The solution can be acidic, the solution can be basic, or it may be neutral. For example, we will take acidic solution where concentration of H plus ions will be more. So for that solution you can calculate pH by using a formula. But in the same solution, even hydroxide ions are also present. Yes, but the concentration of H plus will be far more than that of the concentration of hydroxide ions. Similarly, this thing is applicable for basic solution. In basic solution, of course, OH minus ion concentration will be more. One can calculate pOH. But in the same solution, again H plus ion concentration will be also present. But the concentration of H plus ions is far less than that of the hydroxide ion concentration. And what will happen with the neutral solution? Yes, the concentration of H plus is always equal to the concentration of hydroxide ions in neutral solution, and that's why pH and pOH value will remain equal. Now, as studied previously, we can write the equation Kw is equal to molar concentration of hydronium ion multiplied by molar concentration of hydroxide ion. What is Kw? It is an ionic product of water. The value of Kw is, you know that at 298 Kelvin, 1 into 10 raised to minus 14. Substituting that value in the equation, we will get 1 into 10 raised to minus 14 is equal to molar concentration of hydronium ion multiplied by molar concentration of hydroxide ion. Now taking logarithm on both the sides, we will get minus 14 log to the base 10 of 10 is equal to log to the base 10 of molar concentration of hydronium ion plus log to the base 10 of molar concentration of hydroxyl ion. Now multiplying the both sides by minus 1, we will get 14 is equal to minus log to the base 10 of hydronium ion minus log to the base 10 of hydroxyl ion. Now from the definition, you know that minus log to the base 10 of hydronium ion is nothing but pH. Similarly, minus log to the base 10 of hydroxyl ion is equal to pOH. So we will get the relation as 14 is equal to pH plus pOH. That means for any solution, once you calculate pH, directly you can find out the value of pOH by subtracting the pH value from 14. Similarly, for any basic solution, when you calculate pOH, you can immediately calculate pH of the same solution by subtracting the pOH value from 14. On this, you make it a question, that is, define pH and pOH of the solution, write the mathematical expression for them. Or you make it a question like, derive the mathematical relation between pH and pOH. Now acidity, basicity and neutrality of aqueous solution. First of all, we will take neutral solution. For pure water or any aqueous neutral solution at 298 Kelvin, molar concentration of hydronium ion is equal to the molar concentration of hydroxyl ion is equal to 1 into 10 raised to minus 7 molar. देखो हाइड्रोनियम आयन का कॉन्सेंट्रेशन और हाइड्रोक्सिल आयन का कॉन्सेंट्रेशन सेम होगा और वो रहेगा 1 into 10 raised to minus 7 molar. This is for neutral solution. Yes, that means pH is equal to pOH is equal to 7 for neutral solution. Now we will go to the next one, that is acidic solution. In acidic solution, there is excess of hydronium ions. That is, molar concentration of hydronium ion is greater than 1 into 10 raised to minus 7 molar. Taking log on both the sides, what we will get? Log of molar concentration of hydronium ion greater than minus 7 log of 10. Now, log of molar concentration of hydronium ion is greater than minus 7 because we know that log 10 value is equal to 1. Yes. Now we will take minus 7 on left hand side, so it will become plus 7. Similarly, we will take log of molar concentration of hydronium ion on the right hand side. So it will become negative. Now from the definition, we know that minus log of molar concentration of hydronium ion is nothing but pH. So we can write that 7 is greater than pH. That means for acidic solution, pH is always less than 7. See, keep one thing in your mind. See, for acidic solution, H plus ion concentration is greater than 1 into 10 raised to minus 7 molar. That means pH is less than 7. Whenever hydrogen ion concentration is more, pH will be less. Now for basic solution. In basic solution there is excess of hydroxyl ions. That means hydronium ion concentration is less than 1 into 10 raised to minus 7 molar. Because their hydroxyl ion concentration will be more and hydronium ion concentration will be less. Again, taking log on both sides, we can write log of molar concentration of hydronium ion less than minus 7 log 10. Now as you know, the value of log 10 is 1. We can write log of molar concentration of hydronium ion is less than minus 7. Take minus 7 on left hand side, it will become plus 7. Take log of molar concentration of hydronium ion on right hand side, it will become negative. Now, what we can write instead of minus log of molar concentration of hydronium ion? pH. So, for basic solution, pH is always greater than 7. Yes, you can draw the scale like this. See, from this scale it is very clear. If the pH of the solution is exactly 7, the nature of the solution is neutral. If it lies between 0 to 6, the nature of the solution is acidic. On the other hand, if it lies between 8 to 14, the nature of the solution is basic. Suppose, for example, there are two solutions. The pH of first solution is 6 and the pH of other solution is 2. How will you compare the acidity of the two solutions? Of course, as it is less than, both the solutions are having pH less than 7, both are acidic. But which one is more acidic? The solution which is having pH 2 will be more acidic as compared to the solution which is having pH 6. So from this it is very clear that as you go to left, the solution will become more and more acidic, while as you go to right, that is towards 14, the nature of the solution will become more and more basic, and at 7 the nature of the solution is exactly neutral. On this you may get a simple question like write a short note on pH scale. In the next lecture we are going to learn about hydrolysis of salt, buffer solution, sparingly soluble compounds, relationship between solubility and solubility product, and common ion effect. We are done with today's lecture. I request you to hit the like button and also subscribe my channel. Press the bell icon so that whenever I post a new video, you will be notified. Thank you. Stay home, stay safe.